All right. So today I want to apply the kinds of things that we've been talking about with Green's functions to a very specific and really cool model called the Caldera-Leggett model of friction. So our learning goals today are twofold. One is we'd like to understand how we model friction. So by this I mean the following. We're all familiar with friction. You take something and slide it over a surface, and you hear some noise, and if you slide it long enough, this thing gets hot, and it comes to a stop. Okay, and this is friction. There are in fact two classes of friction here at play. One is called dynamical friction, and then the other one is called static friction. Static friction is the force you need to overcome to get something moving. And dynamical friction is the force that it experiences while it's moving that will effectively bring it to rest. So we've actually learned something about friction, and you will have learned something about friction in your first year physics course, for example, where you would have learned about, let's say, air friction, a particle moving through some medium like air. Experiences a drag force, and you will have learned that this drag force is proportional to the velocity of the object, and that if you jump out of a plane, you don't continuously increase your velocity as you descend. You will eventually hit some threshold velocity called the terminal velocity, and the terminal velocity arises precisely because you have this velocity dependent friction force or drag force that balances eventually your gravitational force until the net force on you, the net vertical force, is zero, and you then hit a constant velocity called a terminal velocity. The key takeaway out of that little spiel is the fact that the friction, the drag force, is proportional to how fast you're moving, right? So it's proportional to the velocity. It's proportional to the rate of change of your position, okay? And this is how friction forces typically arise. In Newton's law, F equals ma, written in terms of, so let's make a note of this. So recall the following. So firstly, there was Newton, and Newton's law tells us the following. It says that F equals ma. If I exert a force on a system, it produces an acceleration. From the point of view of a mathematician or an applied mathematician trying to do something useful, like predict where this particle will be at a later time, it's worthwhile expressing this not in this F equals ma form, but in the form mx double dot minus some driving force equals zero, right? So this here is the typical form of Newton's law. Now, okay, so we have Newton's law, and this typically doesn't account for any friction. If I add friction to this problem, let's try that again. So if I add friction, I get an equation that looks like mx double dot, that's the acceleration term, plus something proportional to, let's call it gamma, x dot, minus this f equals zero. Okay, it's this term here that we're going to be interested in this lecture. All right. The question is, where does this arise from? So by where does this arise from, I mean, can we get a microscopic understanding of this? At this moment, we're treating it like Newton treated the equations of motion. It's a phenomenological thing. You do some experiments, you measure, you add some force to some system, and you measure the effect that this force has on the system, and you can write down a relationship, and you find that the force is proportional to the acceleration. It's a kind of ticker tape experiments that you might have done in high school, right? The force produces an acceleration, and you see that they're proportional, and you see that the constant of proportionality is the mass of the body. Right? In the same way, you can take it and put it on a frictional background, and you'll find that there's a term that's proportional to the velocity, and you add that term to the equation of motion, and there you have it. This is what the effect of friction is. What we want is, as mathematical physicists, to try and come up with a deeper understanding of where such a term might arise from. Okay, so this is what Caldera and Leggett chose to do. The Caldera-Leggett model of friction. So the question that we have here is, where does this come from? Okay, so we would like to come up with a deeper understanding of where such a term could come from. Okay, so I want to illustrate these ideas, and in particular, I want to try and model friction using this using a model called the Caldera-Leggett model. And the model starts from a Lagrangian, and I'm going to assume that everybody is familiar with the concepts of Lagrangians and Euler-Lagrange equations. So I'm just going to continue with this. And the Lagrangian for this, I'm going to write down, and then I'm going to expand it and unpack each of the terms for you. So Q dot squared, the dot here will always mean d by dt, minus omega squared minus delta omega squared Q squared minus Q times sum over I equals 1 to n of Fi Qi plus sum over I of a half Qi dot squared minus omega I squared Qi squared. Okay, so let's unpack each of these things. The dynamical variable that we're interested in is this variable Q. So this is the macroscopic quantum variable that we're interested in. Okay. This term here corresponds to a bath of harmonic oscillators. So we're taking this guy Q, and you should think of capital Q as something like a mass on a spring, and we're embedding it into let's say a bowl of honey, say, right? So the bowl of honey is going to be the bath, and we're going to be simple about this and have a harmonic oscillator bath for good reason. That we embed the system in. And this term here is the coupling. It's a linear coupling term between the oscillator that we're interested in, capital Q, and the bath, the little q's. So this is a linear coupling. Term. Okay, very good. So this is the Caldera-Leggett model, and this is the system we want to study now. So the model clearly consists of some macroscopic variable, Q of t, interacting with a bath of oscillators. Now, this Q of t looks like it's some kind of harmonic variable as well, right? It's got a Q dot squared and something times Q squared in much the same way that the little q's have. Except the frequency here is a little bit funny. So the question that we would ask here is, what is this term here? So where does this come from? Well, the point here is that when I couple the capital Q to the little q I bath, there's an overall frequency shift. So the linear coupling induces a frequency shift. By which I mean the following. Omega, well, omega squared goes to omega squared minus the sum over I of fi squared over omega I squared. Okay. This frequency shift has a very particular effect on the system, which we'll encounter a little bit later. But suffice it to say that I would not want this frequency shift around. So I need to cancel out the frequency shift. So this guy here, this minus omega, sorry. This guy here, minus fi squared over omega I squared summed over the i's, is what I'm going to define to be delta omega squared, so as to precisely cancel out this term. Okay, so this is what we call a counter term. So I add this counter term to my original action, my original Lagrangian, to precisely cancel out this effect. Is everybody with me? And you'll see what will happen in a little bit if I didn't do this. Okay, so now let me give you an exercise. And for this exercise, I want you to use the Euler-Lagrange equations to work out the equations of motion for this system. So using the Euler-Lagrange equations, show the following. Firstly, that the equation of motion for Q reads Q double dot plus omega squared minus delta omega squared Q plus sum over I of Fi Qi equals 0. And the equation of motion for the little q's is that qi double dot plus omega I squared qi plus f I q equals 0. Okay, I'm going to take it for granted that you're going to do this exercise, and it's a useful exercise in just computing equations of motion using the Euler-Lagrange equations. And if you have not studied the calculus of variations in any detail before, then I would like you to inform Nitin about it, and we'll see if we can add some supplementary material on the Euler-Lagrange equations. But if not, and you would like to self-study it, then there's an entire chapter in my notes. I'm going to take it for granted that you're going to do this, and so I'm going to work with these equations of motion. So the first thing to note is that this second equation here is in fact very simple. It's just a forced harmonic oscillator equation. And we know how to solve the forced harmonic oscillator equation using Green's functions. In fact, we worked out the Green's function for the harmonic oscillator. Remember, the Green's function is a measure of the response of the system. So you give it some kick, some delta function kick, and you watch how the system responds, and that's coded in the Green's function. And once you know what the Green's function is, you can then solve the system for any forcing by just writing down a convolution, and that'll give you the solution. So this is just a forced harmonic oscillator. In fact, there are n forced harmonic oscillators, and they're all decoupled, right? So there's a single forcing term, and involving Q, and there's n equations, and I can solve them all simultaneously. So I can use what I know about the Green's function to write down a solution for the second set of equations. So using the harmonic oscillator, Green's function, we'll find the following solution. I'm actually going to write down a solution not for Qi, but for Fi Qi, just by multiplying through by Fi for convenience. This is given by minus the integral from minus infinity to the time t that I'm interested in. The integral is taken with respect to tau. In fact, let me write it like this. So it's Fi squared over omega I sine of omega I times t minus tau q of tau d tau. Okay, so that's the solution for the whole n oscillators in the bath. Okay, let's neaten this up a little bit and define a couple of things that will allow us to make some progress in going forward. So I want to define the following functions. I'm going to define the function capital F of t, and capital F of t is going to be minus the sum over I of Fi squared over omega I sine of omega I times t. And this is called the memory function in the literature. So that in terms of the memory function, the solution, so that in terms of the memory function, the first equation for the macroscopic variable that I'm really interested in, capital Q, can be written as follows. Q double dot plus omega squared minus delta omega squared Q plus the integral from minus infinity to t of f of t minus tau q of tau d tau equal to 0. Okay. Because we're going to need to do some integral transforms, it makes more sense to express the memory function, capital F, in terms of something called the spectral function. And the spectral function, in some sense, is the Fourier transform. It's a Fourier half transform, Fourier sine transform, I guess, of the memory function. So now let's define the spectral function which I'm going to call J of omega. And J of omega is going to be defined as pi over 2 times the sum over I of fi squared over omega I delta of omega minus omega I. So the spectral function is a sum over a set of delta function spikes, okay, in some sense. Each of these delta of omega minus omega I is a delta function spike. In the large n limit, where I have a large number of these oscillators, this is effectively a smooth function because all of these spikes add up, right? And different choices of the spectral function will provide different Bath environments for the system that we're considering. So I specify what sort of bath I'm putting the oscillator into, be it honey or water or something else, by specifying what the spectral function is. So it characterizes the spectrum of couplings, Fi, and frequencies of the oscillator bath. So this guy characterizes this. So this encodes information about the couplings and frequencies of the oscillator bath. All right. And in terms of this spectral function, I can write the memory function, f of t, as minus 2 over pi, integral from 0 to infinity of j of omega sine of omega t dt, d omega, sorry. Okay. So let's go back to the, so this is a, this is a general discussion about spectral functions and memory functions and how we're approaching the system. But if I want to go back to the Caldera-Leggett model, then I have to specify one of these environments in which I put this Q in. So what Caldera and Leggett did was they picked an environment of what's called non-cooperative oscillators. So, for those of you who are Marvel fans like myself, I've always wondered how it is the Black Panther's suit works. Equivalently, you could ask how it is that Captain America's shield works. And the way Captain America's shield works is in vibranium, you have some kinetic energy that impinges on one point in the shield, and all of the rest of the shield acts like oscillators that absorb that energy and then refocus that energy in a particular way. I know I'm talking about fictional characters here, but bear with me. So the point there is that if I take my oscillator and I dip it into a bath that absorbs the energy and that refocuses that energy, then I don't have a dissipative system, right? I've got oscillators that absorb and then cooperate to refocus the energy. This is not what Caldera and Leggett considered. What they considered was non-cooperative oscillators. So I have a bunch of these oscillators, little qi, and they just don't cooperate with each other. So they, the oscillations of Q, capital Q, causes this bath to oscillate. And the bath could certainly refocus the energy, but it doesn't. Okay, so that bath dissipates the energy by absorbing the energy and not cooperating to refocus the energy back onto capital Q. So the non-cooperative bath, a non-cooperative bath is characterized by a spectral function J of omega equal to eta omega for some parameter eta times lambda squared over lambda squared plus omega squared. This lambda here is a cutoff. Okay, the lambda here is a frequency cutoff that is going to regulate the system for us in such a way that integrals are going to converge. Okay, so essentially what we want to do is the following. Remember, we're doing an integral for f of t, we're doing an integral in frequency space. Okay, if we do this integral in frequency space and we integrate out to infinite frequencies, what we'll find is that the integral diverges. So to prevent this divergent integral, what we do is we regulate the integral. And we regulate the integral by adding some frequency cutoff. We say we integrate up to some cutoff frequency beyond which we're ignorant about the system. And we'll get an expression that is lambda dependent. And we hope that its lambda dependence is such that when we send lambda to infinity, that we'll be able to isolate out of this system, out of this answer, we'll be able to isolate some lambda independent part. Okay, this process is known as regularization, and in the physics literature, regularization is one step in a more general process known as renormalization. Any questions?
Jeff, can you please just read off the denominator in that term. I can't, the bar in Zoom is covering it.
Oh, it's lambda squared plus omega squared.
Okay, thank you.
All right. Sorry, just, okay. Okay, is everybody with me?
Yeah, I have one question regarding the memory function. What does it remember? Why is it called a memory function?
Okay, so the memory function codes for us. It codes for us it remembers the way the system behaves for different couplings of the problem. So it basically it's in some sense a memory of the system, and by the system here we mean the bath. It's a historical term that comes from electrical engineering.
Cool. Thank you.
Okay. All right. So we've now chosen a specific spectral function. With this spectral function, we can then go ahead and calculate what the memory function is. Justin, your mic is on. So with an associated memory function, f of t, in fact, I'm going to compute rather minus f of t, equal to 2 over 2 pi I, once I've substituted in for j, integral from minus infinity to infinity of eta omega lambda squared over lambda squared plus omega squared e to the I omega t d omega. Okay, so what I've done is I've expressed the sign of omega t in terms of its real and imaginary part, made a change of variables to write the integral from 0 to omega, sorry, the integral from 0 to infinity as an integral from minus infinity to infinity. And I recognize out of this the sine function, by which I mean SGN, the sine of t, SGN of t. And the sine of t basically just reads off the sine of t. If t is a negative number, it's -1. If t is a positive number, doesn't matter what the number is, it's +1 times eta times lambda squared times, in fact, let me move to the next line. This is equal to the sine of t times eta times lambda squared times e to the minus lambda mod t. Okay. And here we can immediately see that lambda plays the role of a regulator in the fact that it is an envelope to the behavior of the rest of the term. As an exercise, I would like you to carry out this integral. Find an appropriate contour and do the integral. Okay. Once I've done that, I can then move on and compute then the integral that I really care about, which is the integral from minus infinity to t of f of t minus tau q of tau d tau. Okay, which is minus the integral from minus infinity to t of eta lambda squared e to the minus lambda mod t minus tau q of tau. Okay. And I have a question for you, which is, where did the factor of sine of tau go? Sine of t go. I'd like you to think about that in carrying out this integral. Okay, so how do we do this integral? Well, I can't do this integral unless I've specified for you what q of tau is, but q of tau is the variable I'm trying to solve for. So I'm a little bit stuck here. However, what I can do is make a Taylor expansion of q of tau around tau equal to t. Remember, I'm doing an integral in t. Sorry, I'm doing an integral in tau, and I want an expression for q in terms of t. So what we're going to do here is make a Taylor expansion about tau equal to t. And when I do that, and I'll then be able to make an integration. I'll then be able to do the integral term by term. By the way, sorry, this arrow is pointing in the wrong place. I want to Taylor expand the whole thing here. I want to Taylor expand this about tau equal to t. And when I do that, I find that this is minus eta lambda q of t plus eta q dot of t minus eta over 2 lambda q double dot of t, etc. Okay, higher order terms. Those higher order terms will be at least 1 over lambda squared and higher. Okay, the point here is that when I send lambda to infinity, then I expect those higher order terms to vanish. In fact, I expect that in the lambda to infinity limit, even this term here, let me see if this is showing, even this term here, I expect to vanish. This term, on the other hand, appears to be a problem if we're going to take a lambda to infinity limit. So let's see what happens to that term. So notice the following. If I go ahead and calculate minus delta omega squared, which you'll recall, the way I chose my cutoff was to set it equal to the sum over I of fi squared over omega I squared. This is nothing but 2 over pi times the integral from 0 to infinity of the spectral function j of omega over omega d omega. Using the expression that we have for the spectral function, this is just 2 over pi times the integral from 0 to infinity of eta lambda squared over lambda squared plus omega squared integrated with respect to omega, which is just eta times lambda. So that's eta lambda, and this is going to multiply q. So I go back to the problematic term, this guy here, and I see that it's precisely the same term except with the minus sign. So now it becomes clear why we need the counter term. That minus delta omega squared q term exactly cancels the term that's linear in omega. Otherwise, we would end up with a lambda dependent frequency shift, which if I send lambda to infinity is going to cause the thing to blow up. So this term is going to get canceled by the counter term. This term is going to get canceled when I send lambda to infinity. And the only term that actually really matters here in this story is this one. And lo and behold, we have a term that is proportional to the first derivative of q. In other words, when I send lambda to infinity, so in the lambda to infinity limit, then the equation of motion for q is simply q double dot plus eta q dot plus omega squared q. Only now we understand perfectly well where this q dot term is coming from. It's coming from the fact that I take my system, I immerse it in a non-cooperative bath, and the oscillators, the bath oscillators absorb energy from q, but it absorbs it in an incommensurate fashion such that it doesn't, those oscillators don't cooperate long enough to return any energy back to q. And this is how Caldera and Leggett model friction in the system. Any questions? None? Okay, so if there aren't any questions, then let's stop here for today.